Now there is another question that comes. So basically what we are saying is, this is if you like, you can call this as the antiderivative. A function capital F a b to r is called antiderivative of a function f. So one introduces if f dash of x is equal to f of x for every x belonging to AB, right? So that relation that we are saying here, so one gives a name that capital F is the antiderivative of small f, okay? So the question arises, so fundamental theorem of calculus is applicable whenever there is antiderivative for a function, right? You can compute. So the question comes, what are the functions which have antiderivative, right? What is the class of functions, or is there some, you can say that if a function has this property then it will have antiderivative. So we want to answer that question. So question is, which functions have antiderivatives? Keep in mind, antiderivative is not unique, because we are just saying f dash should be equal to f. So if you take f plus a constant, that derivative also will be same. So it is a class of functions. Two antiderivatives differ by a constant, okay, right. So to answer that question, let us first observe a small result. So to answer this, what shall I call? Okay, proposition. So let us say f is a continuous function suppose it is a continuous function, then we know it is integrable, right? Then the claim is there exists a point C belonging to AB such that f of C multiplied by B minus A is equal to integral A to B fx dx. So let us try to understand what is this theorem saying. Because f is continuous, the right hand side integral exists, right? Every continuous function. But what is the left hand side? This is f of C into B minus A. So this is the area of a rectangle with base as AB and height as f of C. So if you interpret it geometrically, it's very nice, in the sense that if this is A and this is B, so this is your function, right? And you are looking at this area below the graph of the function, that is your integral. So this is the right hand side. So the right hand side is right. So this is the right hand side. What is the left hand side? It says there is a point C in between. So there is a point somewhere here, C. So that if you look at this height, so that height is f of C. So this is a rectangle. So look at the rectangle. So area of that rectangle is same as the area, that is the area below the graph of the function. So there is a point C in between in the interval AB, such that if you look at that height and the area of the rectangle with that height, that is equal to the integral of the function. Okay. So this is the reason why it is called this is called mean value theorem for integrals. So this is called mean value theorem for integrals. Why mean value? You can also interpret this. So this the claim star, if you interpret it as f of c is equal to 1 over b minus a integral a to b fx dx, then what does geometrically right hand side represent? Do you think the right hand side looks like an average of the function? F of x is a value at a point in AB, sum up the values, so summation is integral a to b divided by the total number of values, that is the length of the interval. So right hand side can be called as the average value of the function on the interval AB. Right hand side can be called as the average value. So the theorem says if f is continuous, the average value is attained at some point in between. The average value is attained at a point C in between A to B. Okay, so that is another way of saying. So this is, you can call it as the average value. Okay, so and the proof is quite straightforward, because okay, f continuous implies integral a to b fx dx exists, and if I look at this number average value, this is less than or equal to capital M times V minus A, right? Because what is that? That is the, you take the partition with endpoints A, B only, M is the value, right? So supremum capital M on the interval AB, so M times the length. There is the upper sum with respect to the trivial partition, and this is, B minus A, we have taken it down, so let us don't write it there, and less than or equal to small m. Is that okay? M times V minus A is less than the integral, upper sum, lower sum is less than the integral, less than the upper sum. Okay. And the interesting thing is, if I look at this value, this is a number which is caught between the smallest value and the largest value of the function. So what does intermediate value property say? This must be attained at some point, that's all. So the intermediate value property, there exists a C belonging to AB such that f of C is equal to 1 over B minus A to B fx dx. So that implies whatever we wanted to say, that f of C times B minus A is equal to integral A to B fx dx. Right. So there is a point inside the interval, in the open interval AB, right? And while writing the theorem, probably I didn't, I should have said in the open interval A to B. You can specify. Okay, that is what intermediate value property says. If there is a value alpha, there is a value beta, and something in between, then that must be attained at a point in between. Okay, right. So that is intermediate value, mean value theorem for integrals. We will see an application of this in Fundamental Theorem of Calculus Part 2. which says the following, that let f so R be continuous. So let us say f is a function which is continuous. See, actually, okay, what we are trying to do is find out an antiderivative for the function, right? What could be an antiderivative for a continuous function? The fundamental theorem of calculus itself gives you an answer. It says the relation between small f and capital F. If I know small f, I can define what is capital F from this, right? So let us write that straight away, that equation. So let f of x be defined as integral a to x of ft dt, x belonging to AB, right? So for every point x in AB, let us, because f is given to be continuous, so it is integrable. Then this function capital F is defined, okay? Then f is defined and f dash of x is equal to f of x. So this is the function. So this theorem says every continuous function will have a antiderivative. As soon as you are able to recognize the antiderivative, you can get back the integral, right? So a class of all continuous functions have antiderivatives, and for such functions computation of integral is straightforward by fundamental theorem of calculus, okay? So let us just prove that this is the case. So proof. So I have to find a derivative. So let us take a point x belonging to AB. How do I compute the derivative of capital F? What is the definition? F of x plus h minus f of x divided by h, limit h going to 0. So let us look at f of x plus h minus f of x. So what is that quantity equal to? That will be equal to integral a to x plus h minus integral from a to x. I have not stated those properties of integral, namely that the integral is additive over the intervals you, right? So integral from a to c plus integral from c to b is same as integral from a to b, right? So those I will state, so I should have stated that first, but anyway, let us use that for the time being. Namely, this is integral from x to x plus h ft dt. Is that this is integral a to x plus h minus the integral from, so this is x, x plus h, and this is a. So integral from a to this minus the integral from a to x. So what is left is integral from x to x plus h, okay? So that is what we are saying. So f of x plus h is integral a to x plus h minus f of x, that is integral from a to x. So what is left is integral from x to x plus h, right? So let us continue with that. So f of x plus h minus f of x is equal to that quantity. Now look at this quantity. F is a continuous function. F is a continuous function. So it is continuous in the interval x to x plus h also, and just now we proved the mean value theorem. So there must be a point in between x and x plus h, say that this integral is equal to f at that point into the length is h, right? So let us write, okay, before this let us just by mean value theorem, there is a point it depends on h belonging to x to x plus h. Here I am taking h as positive, okay. Just for illustration, h could be positive or negative, x plus h could be on the left side or on the right side, doesn't matter actually. So ch such that integral x to x plus h ft dt is equal to h times f at ch. Right. So put this value in this, so they call that as 1, call this as 2, 1 and 2 imply f of x plus h minus f of x is equal to h times f of ch. So that implies that the ratio f of x divided by h is equal to f of ch. And to compute the derivative, we should take the limit as h goes to 0. So take the limit, so implies limit h going to 0 of f of x plus h minus f of x divided by h is equal to limit h going to 0 f of ch. And what is that equal to? Ch is a point between the interval x to x plus h. H goes to 0, f is a continuous function, so that limit, so c of h will go to x, right. So f of c plus h must go to f of x by continuity of the function f. So that is equal to f of x because of the continuity of the function f, okay. So that proves, so implies f dash of x exists and f dash of x is equal to f of x. I just said this h could be positive or negative, right. If x is the interior point, if x is the end point, then what will happen? You only have on the right hand side, so you only have the right hand derivative. So taking care of that, those are minor things. You can just so you can take x in the open interval, then plus minus doesn't matter, and at the end points you can just have one-sided limits, right. So you can prove for everything. So derivative at the left hand point means it is the right hand derivative, and derivative at the right hand point means it is only the left hand derivative possible. So every continuous function has an antiderivative, and for every function which has antiderivative, integral can be computed. So that is what is the importance of fundamental theorem of calculus, right. So let me give you one application of this fundamental theorem of calculus, which is quite useful or of importance rather. So let me just an application. Of course, it is of great importance, this theorem. It allows you to compute integrals without going into the limit operations, and it has implications in historically in Fourier series and so on. But let us look at a simple application which will all, without knowing Fourier series, you will understand. I think we start using a function called the log function from our school times. I think probably standards 8, 9 or somewhere, a log function, right. What is the definition of log function? We don't know. How is log defined? For us, log is defined by the log tables, okay. Or another example is, what is a trigonometric function? Sin theta. We define sin theta as the height over base. right? But if you want to define sine function as height over base and you want to prove that function is continuous, how do you prove it is continuous? How do you prove that function is differentiable? Because we start using these facts that sine x, cos x all are defined functions, well defined, periodic and so on. Sine is continuous, in fact differentiable, derivative of sine is cos. So if you take the definition of those geometric definitions, you don't get those properties easily. You have to assume those properties. Also the log function is a function which has some nice properties. What are the properties of the log function? Normally we have log of, what is log of AB? Log of A plus log of B, and then we have log of say a raised to power n is equal to n times log A, log of A by B whenever defined we say it is log of A minus log of B and so on, right? Is there any such function with these properties? Does such a function exist at all or not? Not only that, when we come to slightly higher classes, we say log function is differentiable and log derivative is 1 over x. We start using that also, right, without any proof. The reason is that these functions are not easy to define. These functions, for example, if you look at the polynomial functions, right, polynomial function, constant function is a constant polynomial. Function fx equal to x, right, x square, x cube, their sums, linear combinations, all are polynomial functions and you sort of feel comfortable with them, right? You can define them rigorously. You can define a rational function p by q where p is a polynomial, q is a polynomial. But there are functions which cannot be obtained from polynomial functions in any way by any algebra. You have to go to the concept of limits. That is the reason these cannot be defined. For example, you may say that I can define sin x via the series kind of a thing, but that is an infinite operation. It doesn't stop somewhere, right? There is a limit involved in it. So we'll come to series later on. So let me just try to illustrate how fundamental theorem of calculus can be used to define what is called the log function. We will not go into all the details of this, but I will at least initiate so that you can try to prove it yourself, because it's reasonably easy. The clue lies in this thing. The derivative of log is 1 over x. So if I integrate 1 over x, I should be able to get back the log function by fundamental theorem of calculus. So one defines, define ln of x to be equal to integral. Now what is the value of log of 1? That is taken as 0, right? So let us start as from 0 and go to x, 1 over t dt for x bigger than 0, and if it is less than 0, what shall I do? I can only write x to 0, right? So x to 0 but with the negative sign. Okay. Go. Log of 1 is 0. What is log of a negative quantity? 1 is less than 1. What do you think with log of half? To minus log of 2, right? So that's why this negative sign is coming. X to 0, okay, 1 over t dt. And this automatically says log of 1 is 0. log of 1 is 0, right? So I will not go into the details, but let me just say what is obvious from this. Oh sorry, you are right. Bigger than or equal to 1, less than or equal to 1. Sure. Of my oversight. Log of 1 is 0. Right. For negative quantity, log is not defined. It is only defined when x is bigger than. So this is a function defined. So ln is a function defined in 0 to infinity, taking values in R. Okay. It's a function defined only for positive numbers. Log is defined only for positive. Greater than? Less than 1? X is less than 1. What correction she has said, I should have applied it here also. 1 and 1. Log of 1 you want 0, so 1 to x integral, that is when x is bigger than 0, when it is less than 0, right? You can write 1 to x, but normally you write lower limit to upper limit, so with a negative sign. Okay, so that is what, right. So this is a function defined for all positive real numbers. And what is obvious for this? 1 over t is a continuous function. 1 over t is a continuous function. So ln of x is defined. Continuous function is integrable. So ln x is defined. One consequence. Immediately it is defined. And what is the derivative? What is the derivative of ln x? Fundamental Theorem of Calculus. Again, derivative of ln x is 1 over x. That gives you the derivative also. It is differentiable and derivative is 1 over x. Is that okay? 1 over x, 1 to x, derivative is, that is fundamental. Antiderivative, just now we said that. F of x was the integral a to x, so it is 1 to x, so derivative is 1 over x. If the derivative of, so it is a differentiable function with the derivative as 1 over x is bigger than 0, so derivative is everywhere positive. 1 over x derivative, x bigger than 0. So ln x is a function with positive derivative. Go back. I know something about the derivative. What does it say about the function? If the derivative is strictly bigger than 0, the function should be monotonically increasing. So ln of x defined this way is a strictly monotonically increasing function in 0 to infinity, right? And derivative is 1 over x. So what is the second derivative, if you like? 1 over t, derivative 1 over minus, what is the derivative? Minus 1 over x square. X is bigger than 0, anyway x square, derivative is everywhere negative, so it is a concave down function. See, all of your calculus, all those results that we proved, derivative helps you. So it is a continuous function, it is a differentiable function, it is concave down. At 1 it crosses the x-axis, right? Log, and what happens as you go on increasing? What happens to ln of x as x goes to infinity? One can use this itself, 1 over t, to show that as x increases, the area keeps on increasing, right? It goes to infinity. So it keeps on increasing, and one can also prove those other properties that ln of 1 over x. It's very nice actually. One should try to read the proof that ln of, even all those properties, ln of AB is equal to, all these properties can very easily be proved for this definition, okay, and give beautiful applications of calculus basically. So one observes that the graph of this function ln of 1 is 0, so the graph should look like this. It never meets the horizontal and never there is no asymptotes of this is asymptote, but there is no horizontal asymptote. It keeps on increasing. So on this side, as you go this side, the function keeps on going up. So as a consequence of this, ln x is a bijective function from 0 to infinity to r, which is differentiable. So it should have an inverse function. And what is that inverse function? It is the familiar exponential function e raised to power x. So that is the precise definition of what is the exponential function. It comes from the definition of ln of x. So exponential is the inverse of the bijective function ln of x. And one can use to show that because this function is ln x is a differentiable function, inverse function also is differentiable, and derivative is 1 over the derivative of the original function. So you get the exponential is a function which is differentiable with derivative itself. Derivative of e raised to power x is e raised to power x. All this come because of this fundamental theorem of calculus. So you call this as ln of natural base e, then you can define ln of other bases and so on. So that is definition of what is called transcendental functions, and one of the transcendental functions is log and the exponential function. Same way you can try to define what is trigonometric function sine. We can try to apply the same kind of trick. What is the derivative of sine? Cos, but I don't know cos. Okay, derivative of cos is sine, so I am stuck. But what you do is to define sine, it's good enough to define sine inverse. I can define sine inverse in an appropriate interval, say minus pi by 2 to pi by 2. There sine is sine of minus, it goes the value is a 1 function. So if I can define sine inverse, I can define what is sine as the inverse of, like here we are doing, exponential is the inverse of log. So sine inverse, what is the derivative of sine inverse? 1 over 1 minus x square. So that probably we can integrate, right? So one tries to integrate that to get sine inverse and show it has all the nice properties, and the inverse of that is taken as the sine, derivative of sine is taken as cos, and all those properties are proved. So that is the definition, way one uses rigorously fundamental theorem of calculus to define functions which cannot be defined algebraically. Okay, so that is just I am just giving a glimpse. If you feel interested, you should try to read some book. If you want to know a reference, come and ask me. I will tell you the reference where you can read these things. Okay, right. So basically we have tried to define integral. So let me just go back and look at, we looked at integration via upper sums and lower sums, right? There is another way of defining this integral. Okay, so basically what we did was intuitively we tried to capture the area below the graph of the function in lower and upper sums. But and we had to have the condition that if you want to define upper sum, you want to define lower sum, then your function must be a bounded function. Otherwise infimum and supremum doesn't make sense at all.